7, 8, 9, and 10, we did SN1, SN2, E1, E2 reactions. We figured out Hofmann versus Zaitsev alkenes. Then we learned about how to add to alkenes, and we figured out how to make alcohols and haloalkanes and a whole bunch of reactions. Then we learned about alkynes and what kind of additional reactions we can use them for. And in chapter 10, we learn about free radicals. Throughout all that process, we did discuss synthesis. As a matter of fact, on the last exam, I gave you, yes, Destiny, I agree. It's been nonstop since chapter 5. And so this chapter is about synthesis. In the sense, what I've been doing in the last 4 or 5 chapters, talking about synthesis and explaining what synthesis is, but we didn't do it formally, right? You learn how to propose a synthesis, you learn how to figure out how to go from one reactant to a product, whether it's one or multiple step. What we're gonna do today is we're gonna figure out how to think methodically about a synthesis. So when I have a synthesis, what am I supposed to do, and what am I supposed to think, and how do I know I'm on the right track, and or how do I proceed? What you have learned so far, and I hope you learned that, is that for a synthesis, thank you, MD, we start at the product, right? And I want you to know, and I get a couple of students who after the first exam said to me, Professor, on exam day, I was able to solve the synthesis going from reactant to product. And that's fine if the synthesis is only 3 or 4 steps. Sometimes a synthesis could be 20 or 30 steps, and even for an expert, it would be a challenge. So yeah, a lot of people who do organic chemistry for a living can look at a synthesis that's 10, 15 steps and can see right away all the steps in their mind. It's like being a chess master, right? If you're a chess master, you could see the whole game before it starts. In your case, you're not an organic chemistry master. You're still learning. And so you learn one step at a time. And until you become a master, hopefully if you're interested in chemistry and you go to grad school and you become a chemist, organic chemist, then you learn to be more efficient and you can see more steps at once. And so for our purpose, we always going to start at the product and work backward. It's called retrosynthesis. The other thing I want to mention before I start with the slides is that what we have done in the last 4 or 5 chapters, we have accumulated a whole series of different reactions. And these are our arsenal, in your fight against synthesis, because, you have a synthesis, well, we have to use a series of reactions. And which reaction we use doesn't matter. It's not like, let me at random pick a reaction and place it there, right? If you need to make a Markovnikov alcohol, what would you do? If you want to make a Markovnikov alcohol, anybody? We do mercury, oxymercuration, demercuration. So Destiny, yes, Destiny said, oh no. So Destiny, what would happen if you do BH3? BH3THF will give us anti-Markovnikov alcohol. And that's part of the learning process. So you determine what product you want to make, and then you say, I'm going to use this reagent. So let me get started. And just to let you know my plan for the day, and we always do that, I will go through the slides. I do have a few problems on synthesis prepared. And like the typical type of reactions I do in class, the synthesis I have, they increase in difficulty. So the first one is, easy relatively. Then it gets harder and more challenging as time goes by. And the other thing is, I guess I'll let you know now, just like last Sunday, we did a session on mechanisms. Next Sunday, I'll do a session, problem-solving session on synthesis. And I got an email, I guess I should address that. Why did I change the time from 3:30 to 4? Because all my review sessions on Sunday have been at 3:30, and last Sunday it was at 4. And the reason I switched the time till 4, it wasn't personal. It was, you guys had a bio exam, right? You guys had so not all of you, a lot of you had a bio exam, and there was a bio review session on Sunday from 2 to 4, and that's why I changed the time. So yes, on the next exam, there will be a couple of questions about synthesis. And so that's why we're doing this. And what we learned today about synthesis is applicable for the next chapter when we learn alcohols, and also what you learn in Orgo 2. So in organic chemistry 2, you have to go through a synthesis. What you learned today applies to organic chemistry 2. So you could do a synthesis in one step. So it's a simple reaction, right? You have a reactant, and you could form this product, and so convert an alkene to a dibromoalkane, and that's an easy reaction, right? I mean, most of you probably would easily say, we add Br2 carbon tetrachloride. So actually, the author of the book is wrong. It should be dissolved. It's halogenation. Thank you, Destiny. So you add bromine dissolved in carbon tetrachloride. So the idea is that a synthesis could be one step, right? You could make a product in one reaction. As a matter of fact, when you get to Orgo Lab, one of the reactions we have at City College is to make aspirin. And I recall I used to teach the lab, and aspirin is a fun synthesis because you could do it in one single step. And so it's about an hour reaction. Obviously, the more steps you have, the more time it takes. So if you have a reaction that's 15 steps, between the purification and the steps, probably it will take you about a 3-week amount of work, and keep that in mind. All right, so make sure. So the other thing is, and I mentioned that you really have to have a good grasp of what the reactions we have and the reagents, right, to make a Markovnikov, to make an anti-Markovnikov, whether it's an alcohol or a halogen, to make an alkene, whether it's Zaitsev or Hoffman. You really have to have a good understanding of those reactions before you start working on synthesis. So if you're not sure about what a reaction gives, what the product is, before you do a synthesis, you should go back and go over the reactions we covered, because if you don't know the reactions, it's a waste of time to even try to do a synthesis. So for example, here's a multi-step, right? So in synthesis, and I'm going to tell you this, I know there's a slide coming later, there are a couple of things to consider, and I'm going to tell you what they are. One, did you change the functional group, right? Did the functional group change? So in this case, the functional group would be bromine. Did we change it? No, it's still there. Did the location of the functional group change? And in this case, the answer is yes. The other thing, so you could change the functional group on the same place. You could change the functional group position and location, right? The position and the property, like go from bromine to an alcohol. And thirdly, which we haven't really discussed yet in detail, and that's what we're going to learn today, you could also change the skeleton. Now, what does that mean, the skeleton? If you look at the reactant, the bromoalkane, how many carbons does it have? Has 5. And the product has also 5. So a more challenging synthesis, just to let you know, like last exam, I did give you something like this where you had to change the position and the property of the functional group, and you did that. It's more challenging when you have to make the molecule bigger or smaller, usually bigger, by doing a series of reactions and changing the place and the type of functional group. That really is the challenge, and that's what we're going to be learning today. So when you look at the product, and we always work from the end, working backward, how do you make a haloalkene? What do you make a haloalkene from? We make haloalkanes from alkene. Is this addition Markovnikov or anti-Markovnikov? Good. So the blue side is the Markovnikov side. That's the side that has more substituents, right? That's the side that's going to form the carbocation that's more stable. The yellow side is the anti-Markovnikov, right? And of course, How do we make alkenes? We make alkenes from haloalkanes by adding, oh, no, HBr is the addition. You're right. I agree. I'm on the first line, first step. So how to make an alkene? To go from here to here, you guys are right. We add HBr, right? I'm gonna add it since you already mentioned it. It's a Markovnikov addition. If it was anti-Markovnikov, what would I have done? What would have been different about my? It would have been HBr in peroxide, in ROR. All right. Now, to go from this haloalkane to this alkene, is this alkene a Zaitsev or a Hoffman alkene? It's a Zaitsev, right? Because it has more substituents, and because of that, we use a small base, right? So any small base will do. Methoxide would just do the job fine. What would happen if I use a bulky base? What would happen if I accidentally made a mistake and used a bulky base? Where's the Hoffman? Where's the alkene? It will be right there. So using yes, you're right, Eric, good job. So, and the rest of the people who wrote, good job, Javier and Destiny. So yeah, it is, if you use a bulky base, you change the whole structure of the molecule and you end up with a different product. So it's always a challenge for me when I grade synthesis, because a lot of students say, oh, professor, I made a mistake in one step. But if you make a mistake in one step that gives you a product that you can't get, then if that step is the first step, your product is way different than what you actually anticipate. So it's not only important to know the steps, it's important to use the proper, yes, it's like math, right? It's important to use the proper reagent with every step. Otherwise, you're going to end up with a different product. And of course, what I'm going to do today, try to show you how you could work a synthesis and make sure you get the right steps. The other thing, and I've done synthesis before on a smaller scale, what do I always do after I finish a synthesis? What do we always do after you're done with a synthesis? We check, right? We check like it's math, right? Does this step give me this product? If it doesn't, right, you made a mistake, right? So we check each step individually to make sure that the product I get is based on the reagents I used. And so in this case, we use, so obviously the answer is going to be a small base, right? That gives you this alkene, and HBr gives you that haloalkane Markovnikov. Of course, to show you what would have happened if you used a bulky base, well, a bulky base would have given you this molecule. And let's say you made another mistake and you used a HBr and peroxide, then you would have gotten this molecule, which is clearly different than the product that you want, right? And if you're trying to make a drug that cures cancer or something, whatever it is that's important, you don't want to be haphazard in your synthesis. Your synthesis should be precise. Of course, this you all know, if we are here, we can go backward by using HBr and peroxide to get an anti-Markovnikov addition of a haloalkane. So we always start at the product. We go back one step at a time, right? So if we review this again, I have a haloalkane. How do I make that from an alkene? Well, this haloalkane added Markovnikov, so we just add HBr. And of course, from the haloalkane to this alkene, since the alkene is a Zaitsev alkene, more substituents on the alkene, then we use a small base. What if I want to convert an alcohol to an alcohol? All right. Let's start at by the way, it's okay. It's showing you the steps, but it's fine. Again, the first thing I would do, and again, I want to encourage you to do this. Before you do any synthesis, I'm going to remind you of something we did with stereochemistry. Remember stereochemistry back in chapter 5? Before we do assignment of R and S and figure out whether the molecules are enantiomers, or stereomers, what did we do at the beginning? Yes, good times, Robert, good times. We counted the number of carbons to make sure they're not different. In synthesis, you should always, before you start your synthesis, count the number of carbons, because of the carbon count changes, your approach to synthesis change. That's one of the things I don't like about the way the book presents this, because it makes it sound like, oh, start with the product, work backward. It's like a magic trick. It's not a magic trick. It's actually, there's thought behind it. And yes, you can work backward only if the number of carbons in the product and reactant is the same. So if you look at the product, that product has how many carbons? 5. And the first one, the react starting material, is also 5. And so from this alkene to this alcohol, is that reaction producing a Markovnikov or anti-Markovnikov? Destiny, if it's not the same carbons, that's what I'm going to teach you today. You got to be patient, right? You got to give me a chance to get there. So let's learn how to walk, right? And then we can jog a little bit, and then we can sprint. So let's go one step at a time. Because if we start sprinting right away, it's not going to be helpful. And then you all are going to be disappointed and feel like I lost you and I'm going too fast, right? So we want to go one thing at a time. Let's get this out of the way, and then I will show you how to change the number of atoms. Now, so this is Markovnikov. What would you use for Markovnikov? Alcohol formation. We could use acid catalyzed, right? Why does acid catalyzed work in this instance? Why does it work here? Does it always work? Well, it does add Markovnikov. It doesn't always work because often it involves rearrangement. But in this case, we're going to form, and I understand what Christopher is saying, we're going to form the tertiary carboton, which is stable, so we're not worried about rearrangement. However, this is, you got to be careful. You can only add acid catalyzed if you know there is no rearrangement. If there is rearrangement, like you form a secondary carboton, which you know the molecule will rearrange, please do not use acid catalyzed. So what would be the other choice we can use other than acid catalyzed hydration to make a Markovnikov alcohol? HGOAC, it's oxymercuration, demercuration, right? And then it's written right here for a different reaction. So I can go from an alkene to an alcohol by either doing oxymercuration, demercuration, no rearrangement, or acid catalyzed hydration. In this case, it can work because there's no rearrangement in this molecule, in this particular molecule. Can I go from an alcohol to an alkene by using a base? And the answer is no. Destiny. Why not? Why can't I go from an alcohol? It's not a good leaving group. Alcohol is not a good leaving group, because if you add a bulky base or small base, the only thing that's going to happen is the base will, that strong base will deprotonate that alcohol, right? This is an E2. It's not an E1 reaction, right? And so, because E1, why do we stay away from E1 reactions, Camille? Not that I'm saying they're wrong, but why do we stay away from E1 reactions? Because it's not their pool. Often they involve rearrangement, and you can't really judge what so you want to control the product. Now, OH is not a good leaving group. Can I convert OH to a good leaving group? Yes. What do? Add tosylate, OTS, add tosylate. Tosylate chloride, the tosylate molecule, OTS, is stabilized by what? What is it stabilized by? It's stabilized by, yeah, I like that, it's resonance, you're right. It's stabilized by resonance. And so that makes it a good leaving group. So you take the alcohol, you add TSCl, that converts the alcohol into, I'm going to draw it because it's missing here. This is a very good leaving group, right? It's a very good leaving group. Now I can add a small base to get the Zaitsev alkene. And so, of course, if you add a bulky base, what would you end up with? Well, here at the bottom, they're showing you the wrong things. If you did add a bulky base, you would end up with the Hoffman alkene, which now that's not what we want. And if you make the mistake of using BH3 THF, again, it depends what the product is, right? If this is what you want, right? If this is what you want, what kind of base you use, and whether we do oxymercuration, demercuration, or a hydroboration oxidation, I get a different product. And again, all these reactions so far, what they've had in common is the number of carbons remained the same, right? That's really important, because what's going to happen next, I'm going to show you what happens when we change the number of carbons. Again, first thing I would do is count the number of carbons. Number of carbons in the reactant and the product. In the reactant and the product. How many? 7. 7 in both, right? That means the number of carbons didn't change. So we don't have to worry about making the molecule bigger or smaller or whatever, etc. And I will show you that in a little while. Now, we went from an alkene to an alkene. We changed the functional group. It's still the same functional group, but we changed its position, right? So let's start at the product. We always start at the product. What kind of alkene is this? We get alkenes from haloalkanes. That alkene, thank you, Robert, and Eric, and Pizza, you're all right. It's a Hoffman alkene. It's a Hoffman alkene because it has only 2 substituents. And how do you make a Hoffman alkene from a haloalkane? We use a bulky base. All right, so great. Now, see, done with that step. And now we go to the middle portion. How do we make a haloalkane from an alkene? The question is that haloalkane? You're right. You're absolutely right. But let's think about why we're adding HBr, right? You're all right. It's HBr because it is a Markovnikov addition. Right? If we wanted to, like for example, here, let me show you. What if I wanted you to go from here? Let me try to draw this molecule. Let's say this is my product. What would have been different? It's the first step, right? Because this is also a Hoffman alkene from this haloalkane, and to that we add a bulky base. Same bulky base we're going to use on top. And the question is, how do you go from this molecule to this molecule? Well, that's an anti-Markovnikov addition, and because of that, Serena, you're right, we add HBr in peroxide, which is RO. So that's, one way to learn synthesis is to play around with synthesis. Like have your starting reaction, right? A reactant, and do like few of the reactions, reaction A, reaction B, reaction C, and you do a series of reactions, you get the product, right? Now pretend that you don't know what just draw the reactant and the product, and now work backward and try to figure out what the steps in the middle are, right? You came up with them. But it's not as easy as it sounds, especially when you do, 7, 8 steps, you guys tend to forget. And then you cheat and you look at your sheet and you're like, oh, I should have known this. And then you complain because you did your own exam too hard. Just like you blame me for making the exam hard, right? All right, so HBr gives me the Markovnikov addition, and a bulky base will give me a Hoffman alkene. Anything else produced a different one-step synthesis are called reactions. I will give you a couple of reactions on the next exam. So how do you go from an alkane to an alkene? So we start at an alkene, right? So how do you make an alkene? What method have you learned so far that you can make an alkene? Now, I want to remind you, yes, you could say, I learned how to make an alkene from an alkyne, but can you have an alkyne inside a ring? And the answer is no. Robert, we're not I'm not saying you're wrong, Robert. You're actually right. But remember, we start a synthesis. Where do we start? The product at the end. I mean, I'm not saying you're wrong, but you're working from the reactant. So the question is, how do I make an alkene? We make alkenes from haloalkanes. And is that alkene a Hoffman or Zaitsev alkene? It's a Zaitsev. So all we have to do add a small base, right? Small base. Now, from an alkane to a bromoalkane, and that was chapter 10, by the way, I explained to you. What you do is, it's a free radical reaction. You add Br2 in light, with light. And the bromine will add to the alkane at the place where we can form the most stable free radical. And why did the bromine add there? Because let's look at them. If I form a free radical here, what kind of free radical would that be? Primary. If I form my free radical here or here or here or here, or here, all these are equivalent, that's secondary. However, if I form a free radical here, that is tertiary, and that is the most stable free radical formation, and that's why the bromine adds there. And once you know that, so you convert your alkane to a haloalkane, and then the haloalkane can be made to an alkene. And by the way, this alkene, right? Remember, think about what we did on the last exam. You could make a whole bunch of things out of this alkene, right? You can make an alcohol, you can make a haloalkane, you can make an aldehyde and a ketone by doing an oxidation with ozone. There are a whole bunch of reactions, or I can make a dibromoalkane, I can make a diol. So once you get to the alkene, there are many, many possible products you could make based on that alkene. Kind of review, as I said, the good thing about this chapter, a lot of this stuff is kind of a review. If you have an alkyne and we add Lindlar's catalyst to it, what do you get? We get a cis alkene. We get a cis alkene. If we have the same alkyne and we add sodium in liquid ammonia, that will give me a transalkene. So that's important, because if you want to make a cis or transalkene, that depends on your starting material, right? So if you have an alkyne and you want to make a cis alkene because so what would be an example where I'll have to make a cis alkene? If I want to do an SS dibromoalkane, then we need a cis alkene. Right? If I have to do an RS, then we do a trans. And so that's important to differentiate. And so it all depends on what your product is. Now, if we have an alkene, and stay with me here because I want to explain what this is. If we have an alkene and we add bromine and carbon tetrachloride, what would happen? What would the alkene turn to? It will turn into a dibromoalkane, where they're anti. It's not trans. I mean, I understand what you mean, Destiny. You mean the bromines are on opposite side, right? And I'm gonna get away with it because trans applies only to alkenes. So the bromines add anti, they add on opposite side. And what happens when you have dibromoalkane, right? Yes, the correct way is anti, because trans applies to to cis and trans where you have an alkene or a ring. What happens when you have a dibromoalkane and you add excess NaNH2 followed by water? That will give you the alkyne. So you could use an alkyne to make an alkene. Okay, Christopher, I'll answer that question. Let me just finish with my train of thought. You could use an alkyne to make an alkene, but also if you have an alkene, you should be able to make an alkyne. I'm not saying in a synthesis, go from an alkene to an alkyne, back to an alkene, back to an alkyne. That would be silly, right? You're working in a circle. What I'm saying is that if you have an alkyne, you should be able to make an alkene out of it. And if you have an alkene, you should be able to make an alkyne. So, Christopher, if you have an alkyne, so let's start with alkene. If you have an alkene and you add Br2, how many pi bonds do you have? We have one pi bond. So how many bromines can we add? Two. And so we get two halogens, right? Two bromines, two chlorines, two iodines. If we have an alkyne, how many pi bonds does the alkyne have? It has two pi bonds. That means if I add bromine, and each pi bond can take in two atoms. So if I add bromine or chlorine or iodine, I will end up adding four of them. Does that answer your question? I think that's what you were asking. And of course, if you have an alkyne or an alkene and you add hydrogens in the presence of a catalyst, you will end up with an alkane. In theory, that's great. In reality, it's not, because alkynes and alkenes are more expensive. Of course, to go back to free radical reactions, when you have an alkane and you add bromine and light, you will end up with a halogenated alkane, where the halogen adds to the site where you can form the most stable free radical, whichever one is that. And of course, once you have that with a base, you end up with an alkene. Actually, you know what? It's towards the end of the semester. Let's see if you've learned some stuff. If I take that molecule and add Br2, I will end up with, if you take this molecule and add NaOCH2 CH3, what do you end up with? Don't feel bad. What kind of reaction is that going to happen? Thank you, Jimmy. It's an SN2. Why is it SN2? It's a primary substrate with small base. You get an alkene. Small base, strong nucleophile. Would you get an alkene with this reaction? Okay. Actually, this is not true, not for that molecule, right? See, you know more than people who make slides. Remember, I told you, like, you'll figure out you learn organic chemistry when you can read the textbook and find things that are wrong with it. Then you really learn organic chemistry. So if you look at this, I know a lot of you figured it out. So don't look at the product and say, oh, well, you know, I know a lot of you wrote Zicep because you were trying to impress me because you know it's an alkene. It's not an alkene. It's what the author thinks it should be, but it's not. All right, so what happens now? That's because Destiny asked me before, well, what do we do? What happens when we change the carbon skeleton? When we change the carbon skeleton, well, how do we change the carbon skeleton? Well, you either make the molecule bigger or smaller. And I'm going to tell you up front, so most synthesis, you want to make the molecule bigger, right? You're trying to, it's like building a house, right? You don't take a big house and take some machine and cut it down to a small room, right? That I don't think, I mean, if you want to, you can, right? If you want to have less cleaning and less work to do around the house, you can. But usually what people do is in synthesis, you make bigger molecules. That's what synthetic organic chemists do for a living. They take a small molecule and they make something out of it, and then they make it bigger and bigger, and they add different functional groups until it becomes something that is exactly what they're trying to And so, yes, so for our purpose so far, the best way we know how to make molecules bigger is what we learned in chapter 9, and that is by using acetylene, right? So acetylene is important for us. It's not the only way, by the way. When I cover chapter 10, 12, I will go through alcohols, and I'll show you Grignard reagents, and you'll learn alcohols are more versatile than acetylene. It doesn't mean that acetylene is useless. No, it is. You could do a lot of things with acetylene, and you could make certain products. But when we get to alcohols, you'll learn that there are other ways of making a synthesis. And you could, by the way, on a third exam, I might give a synthesis where two students have, one of them might have used acetylene to solve, another one used alcohols to solve, and they could both very well be right. Or they could be both wrong, right? I hope not. I want you to be right. I want you to learn how to do a synthesis, not get synthesis wrong. And that's important, because if you have a synthesis, all I care about is that when I grade you, is not that whether you did it the way I would do it. Obviously, there are certain things I look for, right? I mean, if a synthesis can be done in 2 steps, and it took you 45 steps to do it, I'm not impressed, right? I mean, I'm not going to give you a 0, but that's not a, optimum. If it takes you 5 minutes to do a job, and somebody else will do the same job in 4 hours, that's not good, right? And so, yeah, I look for certain things, but you don't have to solve it the way I would solve it, whether you use an alcohol or acetylene. So first, we look at the carbon skeleton, right? Whether it either increased in size or decreased. And based on what we learned so far, we increased the size of the skeleton based on SN2 reactions. And I'm going to stress the importance of acetylide as a molecule that can add 2 carbons, right? Just if you want to, I mean, obviously you could say, what about if more than 2 carbons? You could replace the hydrogen with a methyl or ethyl or propyl, but you could add a molecule by SN2 to any haloalkane. But there is a catch. The catch is, what's the catch? The haloalkane must be what? Like, I'll give you an example. This is a haloalkane. This is a haloalkane. This is a haloalkane. Can I do 2 reactions with all 3? No, I can only, you're right. It has to be primary. It has to be primary. That means I can't do SN2 reaction with this or this one because it's secondary or tertiary, because acetylide is a good nucleophile, but it's also a powerful base. And when it has a choice, it will react as a base. So with secondary or tertiary, it will be an elimination reaction, not a substitution. So the only catch is that your substrate must be a primary substrate. I don't know what I would call that terminal, but it's a primary substrate. All right, and so we make the molecule bigger. When changing the carbons, I don't understand your question. Oh yeah, so if not always, if you use an acetylide ion, since it's going to be an SN2 reaction, the substrate must be primary. Obviously, later on, when we get to chapter 12, you could use secondary and tertiary and add to them, but you use Grignard reagent, which is a whole different type of reaction, and I haven't taught you yet. But if you have a primary and it's growing linearly, it's easy to do SN2, and you could also do alcohols, which I will show later. So for example, this is a primary substrate, right? Primary substrate. X is a halogen good leaving group, chlorine, bromine, iodine, either one of the three. There is my alkene. This is a very powerful base, but it's also a good nucleophile. And with primary substrates, it will go as SN2. And so now we have 4 carbons, and this is 3, and we end up with a 7-carbon molecule. And so, that's a way of building molecules and increasing the size. That doesn't change the functional group because we start with an alkyne. But the good news is, if we know we have an alkyne, there are things we could make out of alkynes. Right? I could convert an alkyne to an alkene, which then I could make an alcohol. I could take an alkyne and make it into a ketone or aldehyde. Remember those reactions from last class? So yeah, there are function groups we can make using the alkyne. So here's an example of a molecule where you change the carbon size into a smaller number, right? We went from 1, 2, 3, 4, 5 carbons to 1, 2, 3, 4 carbons. And so we had an alkene, we add ozone, and what happens when you add ozone? Break the bond in the middle, you form aldehydes and ketones. Yes, crack it. It cracks it right there. And you can make aldehydes and ketones, and in this case, we made 2 aldehydes, and the size of the molecule decreased. So just letting you know that there are ways, there are times you might want to make the molecule smaller in size, and that's one way of doing it. So when we do a synthesis, first thing we look at, did the carbon skeleton change? Is it gaining or losing? Usually it's gaining. How many atoms did we add, etc. And the second thing is that, did we change the identity and the location? So we start with bromine, we end up with alcohol. Is the bromine or the alcohol on the same carbon? Is it on a different carbon? And if it is, there are steps we have to do. We can't just say, put an arrow and say, well, it's that carbon, this carbon, same thing. So we have to go through this process every time. We go from the end to the beginning, but while we're working backwards, I'm thinking in the back of my head, did the carbon skeleton change? And did the functional group change? And where did it change to? And so, for example, if you look at this molecule, right? How many carbons on the reactant? 5, okay. Product? 7. So clearly, I would say the number of carbons changed, right? So that's one. The second question is, did the functional group change? Yeah, we went from an alkyne to an alkene. I do have I'll show you what the author has, because I would like to do my own. So in this case, we did change the skeleton, but we also changed the function groups. And if we start at the product, what would you say this product is? If I ask you to describe that molecule, I know it's an alkene. What else is special about that alkene? It's a transalkene. Thank you, Robert. And how do you make a transalkene? From an alkyne by using sodium in liquid ammonia. So thinking backwards, and I'm not going to solve this, I must have an alkyne here, right? And add sodium in liquid ammonia. And then how can I get to this alkyne? That will be the next step, and we'll work it out. So if we have an alkyne, so let's start at the end. At the end, from the last step, alkenes, trans, from an alkyne are made with sodium and liquid ammonia. If this was a cis-alkene, the only difference would have been in this step, I would write Linder-Scatters. So that would be going backwards. This is the last step. How do you make this alkyne from this molecule? It's, by the way, 1, 2 means 2 steps. That's 2 separate reactions. What happens when you have a terminal alkyne and you add NeNH2 to it? You will deprotonate it to form the alkanite. And then this molecule, when you react it with ethyl iodide or ethyl bromide or ethyl chloride, it will add how many carbons? Well, ethyl is 2, so it will add 2 carbons. And the molecule will grow in size. So a lot of times people like to write those as 1, 2, 3. On my exam, you could separate them as each step, and it's fine with me. I'll grade them correctly either way. So in this case, this is a 3-step synthesis. First, we add NeNH2 to deprotonate the alkyne. Then we add ethyl iodide to have an SN2 reaction where we add 2 carbons. We still have an alkyne. Then we add sodium and liquid ammonia that will convert the alkyne into a trans alkene. Again, you've seen this before. We work from the last step and we work backward. We always ask the questions, is the skeleton changing? Is the functional group changing and or moving? So is it bromine to an alcohol? Is it in the same place or is it somewhere else? Count number of carbons. So answer the first question. Is the skeleton changing? No, because we have how many carbons? 6 and 6, right? 6 and 6. So the number of carbons stayed the same. So I don't have to worry about making the molecule bigger. However, obviously, from an alcohol to an alkyne, do you know a step 1 reaction that can convert an alcohol to an alkyne? The answer to that is no. But how do you make an alkyne? How do we make an alkyne? From, it's excess what? It's not from an alkene. There's a step in between. We make an alkyne from, what do you add NeNH2 except to what? To dibromoalkane. Dibromoalkane. I'm going to show you. That means this alkyne, I can make it from dibromoalkane, alkane. And when I make it from dibromoalkane, I'm going to show you the different possibilities. Would you use this dibromoalkane or this one or this one? Or does it matter? Why not red or green? I'm not saying, Christopher, that you're wrong. What I'm saying is that you said blue. Actually, Muhammad is correct. Actually, I'm going to tell you. You know how to make those molecules? You know how to make the red molecule? You make the red molecule from an alkyne by adding HBr. You make the green molecule from an alkyne by adding HBr in peroxide. So basically, if you decide to use the red one or the green one, yes, you could use it to make an alkyne, but where do you get this molecule? You get it from an alkyne. But you're back to the alkyne. You really haven't done anything, right? So again, another thing to think about is if you can only make a certain molecule from the product you want, and then you make the product from that molecule, but then it's kind of like, think about it, you're going in a circle, and that's another thing to consider. So I know most of you kind of said the blue. Why the blue? The blue, because I can make that molecule, and I know a lot of you said when I said how to make an alkyne, you said from an alkene. I could make this molecule from an alkene. And that's why we use the blue one, because if we use the red one or green one, well, it's fine. It will give me the alkyne, but the way we can get those molecules are from alkynes. So it really is kind of like those reasoning that doesn't work out. And so the author doesn't explain that, but it doesn't matter now that you understand it. So we make the alkyne from the dihaloalkane. So dihaloalkane with excess NeNH2 followed by water. And a lot of you wrote that you get that alkyne. How do you make a dihalogenated alkane? From yeah, you're right. Br2 with it's absolutely correct. Br2 with carbon tetrachloride to what? To an alkene. And then can I take an alcohol and make an alkene out of it with a strong base? Nope. Destiny. Don't agree with me. You don't know me. Because alcohol is a very bad leaving group. So what you have to do is, so there is a step where we have to convert the alcohol into a good leaving group. And on which one is that? Thank you. It's not protonate. It's react with DSCl. Protonate means we're adding a hydrogen. We're not adding a hydrogen. We're converting it to stacylate, and that's a good leaving group. Now you got it, Destiny. So the bromine, the dibromo compound, we can get it from an alkene, right? That's easily. And the question is, so now we're going back one step. So we start with the alkyne. The alkyne we make with the dihaloalkane. The dihaloalkane we can get from an alkene. Well, how can I make this alkene from this alcohol? I just explained to Destiny that we have to convert the alcohol into a good leaving group. If this was a bromine, then it would have been a lot easier, obviously. So what you do is you convert the alcohol, and here are the steps, into a good leaving group, TSCl, right, tosylate, and then use a bulky base. By the way, DBU or DBN, if you'll go back to chapter 7, these were the bulky, some of the bulky bases. You don't have to use this. Guess what? I would use terbutyl oxide, right? And then you make an alkene, and then the alkene with bromine and carbon tetrachloride can give me a dihaloalkane, which then I can make an alkyne out of it. You panicking yet? Okay. Don't worry, I do have about 6 or 7 problems I pre-prepared. So this is now, and then you could write it all together in one step. Sequence. Step 1, tosylate chloride. Step 2, terbutyl oxide, which is the bulky base. Step 3, Br2 in carbon tetrachloride, then excess NaNH2 followed by water. So this would be the summary of all the different steps. An important thing, I guess, this is 2021, we have to think green. So prevent waste, right? Brain is burning. Okay. So clearly when you do an organic synthesis, you got to think about what products you have, side products. Like for example, prevent waste, use less hazardous substances. I'm going to go through all of these. Use safer solvents and maximize atom economy, basically. Try to use reactions that the ratio is 1-to-1 and you don't get a lot of leftovers. I'll show you an example in a couple of slides. So here's one where atom economy, right? Atom economy. If you do acid catalyzed, you end up with a product which is the same as this. If you do oxymercuration, demercuration, all these in red are leftovers. Now I want to tell you something about leftovers. So BH3 is this, okay, it's not that hazardous to the environment. Mercury is really hazardous to the environment. Yeah, going from an alkyne to an alkane is not green chemistry. It's a waste of chemicals, right? So mercury is hazardous, and you can't just throw it down the sink. You have to dispose of it properly. And so a lot of times when you have reactions that involve molecules that are hazardous, maybe you should, if you can, sometimes you really have no choice, then you use it. But if you can use an alternate, do so. Another example is, like I showed you in class in chapter 8, like OSO4, right? Osmium tetraoxide gives us a diol sin. Remember that? What else will give me a diol sin other than azimuth tetroxide. KMNO4 is a lot. OSO4, osmium is one of the most poisonous chemicals, and so it's hard to discard off. You have to be careful when you're using it. So all these things are part of what you would consider when you're running a reaction or a synthesis. Obviously, use catalysts because that would speed up the rate of reaction without having to use a lot of chemicals. Try to run reactions at room temperature so you're not heating and using electricity. Of course, you could use renewable feedstocks. You can get chemicals out of grains and corn. I don't know if you guys know that. You can convert corn into gasoline or ethanol that they add to gasoline, so you can get a lot of chemicals that are renewable. So again, when we do a reaction, make sure you look at the skeleton, whether it changed, and see what happened to the function group, whether it changed, and if it also changed the location. So if you want to practice, and I told you that, like, start with a simple reactant and like do a whole bunch of reactions. And if you have a friend, what you could do is one person can do a reaction, like do like 5-6 steps. Don't do like 50 steps. And then give just the reactant and the product to your friend that you know what the steps are, and have them reciprocate. Then you can work backward and see whether you learn. So if you study in a group, this will be a really good way to practice synthesis. So for example here, so this is a practice, right? So I have an alkyne, I added NaNH2, that gives me a acetylide ion. Methyl iodide will add a methyl. Then I take that molecule, I do another NaNH2 and another methyl iodide. That gives me now, so the molecule now grew in size. And if I add Linder's catalyst, I will end up with an cis alkene. And then you can give your friend this reaction and say, could you do a synthesis? You know what the answer is, right? And so they have to work backward and figure out whether they can do that particular synthesis. And that will be a good practice for you. Keep in mind that sometimes if you do 2 steps versus 1, right? Like for example, here's an alkene, BH3THF followed by H2O2 and OH is one simple reaction that gives you an alcohol that is anti-Markovnikov. However, you could accomplish the same reaction by doing HBr in peroxide. What would happen when you do HBr in peroxide? What happens when you do HBr in peroxide? We end up with a anti-Markovnikov bromo addition. If you have that molecule and you add OH minus to it, what kind of reaction is that? It's an SN2, right? The pair of electrons on the oxygen will attack this primary substrate and the bromine leaves. That gives me this product. So there's this is what I was talking about earlier, is that sometimes 2 people might have 2 different ways of producing a product, and both ways are correct. This is the last slide. Yay. It's that time of day, almost 4 o'clock. I get kicked out of Blackboard every class at, yes, it's example time, at 4 o'clock. All right. So as I said, I prepared a few problems, and I'd like to see if I can go through